Hi everyone. In this video, we will discuss multiple regression and how to conduct multiple regression analysis using SPSS. The multiple regression method is used when we have one metric dependent variable and multiple metric independent variables. In this example, we will use each batch dataset for the analysis. The dependent variable is X19 customer satisfaction, and we have 13 independent variables x6 to x18. Before testing the assumptions, we need to make sure the sample size is sufficient for this analysis. The required sample size for multiple regressions is determined based on the number of independent variables, test power, and expected significance level. The details on sample size determination for this test are discussed on page 174. The general rule is to have a ratio of observations to independent variables of at least 5 to 1. Table 4.5 in the textbook indicates the minimum R-square that can be found statistically significant with a test power of 0.8, the significance level of 0.01 or 0.05 with different number of independent variables and sample sizes. In this example, we have a sample size of 100 observations, which meet the minimum ratio of observations to independent variable, 5 to 1. In addition, a sample size of 100 with 13 independent variables can detect a relationship with R-square values of about 23% and a power of 0.8 with a significance level of 0.01. If we use a significance level of 0.05, the minimum R-square is 18%. These numbers indicate that a sample size of 100 is sufficient for this analysis. As for assumptions, multiple regression requires linearity, homoscedasticity, independence of error terms, and normality. We have tested these assumptions in other videos, so we will not do it again here. Missing values and outliers also need to be detected and handled. As we noted in the normality video, transformation has been done, but transformed variables make the results interpretation harder. In this example, we will first run the analysis with the original data, then repeat the process with the transformed variables and compare the results. When you have a large sample size, it is also recommended to split sample into test sample and validation sample for the validation purpose. The process is exactly the same. In this example, we will not split the data and we will run the analysis with the entire dataset. To run multiple regression, we go to Analyze in the menu, select Regression, and then choose Linear. We will add ID variable to case labels, which is to show case IDs. Then we add X19 as the dependent variable to the dependent box. For independent variables, we add X6 to X18 to the independence box. The estimation method needs to be selected. We have several options here. Stepwise estimation is the most popular method in which variables are selected to be included in the model based on the incremental explanatory power they can add to the model. Independent variables are added as long as the partial correlation coefficients are statistically significant. A variable may be removed if its predictive power drops to a non-significant level, while another variable is added to the model. Forward and backward addition are trial and error processes for finding the best regression estimates. Forward addition method is similar to the stepwise in that it builds the regression equation with a single independent variable and continues to add variable to the model. On the other hand, Backward addition method starts with all independent variables and deletes variables that do not contribute to the model. The major difference between the stepwise and these methods is that the stepwise is able to delete variables at each stage. With forward or backward addition, once a variable is added or deleted, the action cannot be reversed at a later stage. In this example, we will use the stepwise estimation method. Click Statistics option and we will make some selection. We check estimates to receive the regression coefficients, check model fit and R-square change to see the model fit's results, and check collinearity diagnostics to check the multicollinearity issues. Multicollinearity occurs when a single independent variable is highly correlated with other independent variables. These issues must be evaluated carefully since it may affect the results. Then we select plots. We check normal probability plot, which will show the standardized residual plot that compares predicted and observed values. In this example, we do not make any selection in Save and Options. Click OK. Running the multiple regression analysis is very straightforward, but interpreting the results is challenging. First, let's look at the model summary, which shows the model fit and changes throughout all steps. R-square is coefficient of determination, which indicates the percentage of total variation of the dependent variable explained by the model. Adjusted R-square is R-square value that takes into account the number of independent variables and the sample size. F ratio is derived from the ANOVA table and is used to test the hypothesis that R-square is significantly greater than 0. Standard error of the estimate is a measure of the accuracy of the prediction. The variables enter remove table shows specific variables entered or removed at each model. For example, in model 1, X9 is added. Then X6 is added in model 2. Other variables that are included in the regression model are X12, X7, and X11. The remaining variables are excluded from the regression model. As discussed before, the stepwise method selects the most contributive variables to add to the model. We can see the changes of R-squared throughout 5 models of the stepwise process. R-squared has improved from 0.364 to 0.791. Adjusted R-squared also shows the improvement throughout all steps. In addition, the standard error has reduced significantly from 0.955 to 0.56. F ratios for the final model is also significant and further support the model fit. Note that the stepwise process stops at step 5 because after that, adding any variable will not improve the model fit. Now we have the final model. We need to interpret the model itself. We have B, which is unstandardized coefficient, standard error, standardized coefficients, t-value, and significance level. Note that we have the intercept or constant value with unstandardized coefficients. The unstandardized intercept and coefficients are used to write the regression equation. However, using standardized coefficients allow us to compare the effects among independent variables. We will only examine the regression coefficients for the final model. The significance levels show that all of these relationships are significant. If we form hypotheses for these relationships, we can conclude that these hypotheses are supported. We can note that most independent variables have a positive effect on the dependent variable, which is customer satisfaction, except for X17, which is e-commerce activities. Thus, we can conclude that the higher the complaint solution, product quality, sales force image, or product line, the higher the customer satisfaction. On the contrary, the higher the e-commerce activities, the lower the customer satisfaction. Using the standardized coefficients, we can compare the effects of these predictors on the customer satisfaction to determine the importance of variables. Specifically, X12 has the highest impact on the customer satisfaction, followed by X6, X9, and so on. Next, we need to evaluate the impact of multicollinearity since this may affect the regression results. We examine the collinearity statistics in the last two columns. In this case, we have tolerance and VIF, or variance inflation factor, as two measures of multicollinearity. Tolerance is the amount of variability of selected independent variable not explained by other independent variables. The high tolerance value means a small degree of multicollinearity. The suggested tolerance values is greater than 0.1. VIF refers to the effect that other independent variables have on the standard error of a regression coefficient. VIF is expected to be less than 10 to ensure the acceptable level of multicollinearity. In this example, all tolerance values are greater than 0.1 and all VIF values are less than 10, so multicollinearity should not be the concern. The excluded variables table shows us variables that are excluded from the analysis and the final model. In other words, adding any of these variables to the regression model will not contribute to the model, and they do not have a significant relationship with the dependent variable. We will examine the normal plot of regression standardized residual. On x-axis, we have observed values, and on y-axis, we have expected values, both in terms of cumulative probability. As you can see, the values fall along the diagonal with no substantial or systematic departures. Thus, the residuals are considered to represent a normal distribution. That was the regression analysis with the original dataset. As mentioned before, we will run the regression analysis again with the transformed data and make the comparison. The entire analysis process is exactly the same. We only change the dataset. Here are the results, and let's take a quick look. This is a stepwise regression model with a transformed dataset. We have the same variables in the final model. The model summary shows very similar R-square values and adjusted R-square values. The model fit is still good with significant F-test, and the standard error is very similar with the previous results. In the final model, we have the same predictors: X9, X6, X12, X7, and X11. The tolerance and VIF values also indicates no concern with the multicollinearity issues. The normal standardized residual plot also shows a normal distribution as before. To make the comparison between two models easier, I copy the regression coefficients of these two models with original dataset and with transformed dataset in the same Word document. Note that among the predictors, X6 has been transformed using square and X7 has been transformed using logarithm. Let's examine the unstandardized coefficients. For X9, we have 0.3910 and 0.309, very close. For X6, we have 0.369 and 0.024, but X6 has been transformed using square, so the difference is understandable. For X12, we have 0.775 and 0.761, also very close. For x7, we have negative 0.417 and negative 3.561. The sign is the same, but the value difference is due to the transformations of x7 using logarithm. For x11, we have 0.174 and 0.169, also very close. Note that when we interpret the effects of the predictors for x6 and x7, which have been transformed, we cannot interpret the same way since the data is not original. The standard errors are very similar between these two models. As mentioned before, in order to compare effects of predictors on the dependent variable, standardized coefficients should be used. So let's compare these standardized coefficients between these two versions. We'll focus mainly on two transform variables, x6 and x7. For x6, we have 0.432 and 0.433, very close. For x7, we have negative 0.245 and negative 0.244, also very close. Thus, in terms of standardized coefficients, these two models are very close. In this case, we can argue that transforming variables does not have substantial impact on the results, and we might be able to use the original data set for the analysis. However, to confirm the model, it is recommended to split the sample into test sample and validation sample and compare the results in order to validate the regression model. That is how to conduct a multiple regression analysis using SPSS. Thank you and bye now.